As it was mentioned, I'm from Dubna also. I work with Vahagn, with Martin. They presented a lot of information today, and you will see some overlaps. But the more you see, the more you understand. So I mean, that's even better and easier for me. So the title of the work is on classicality of qudits on low-dimensional orbits for various metrics. So I will consider also the global indicator of classicality, or quantumness, as you wish. And I will say some common words, but I will consider an example of a three-level system called qudit. And I will try to calculate the global indicator for that example, but for low-dimensional orbits. Why low-dimensional? Because it's just it's also an interesting case, and it was possible to calculate it analytically, so we just decided to do it so. But of course, you can calculate it in general, and it's done, but yet it's only numerical. So here's the outline of my talk. I will give you some objective. Так, кнопка не работает, да?
Нажать и прям держать.
Ага, все хорошо. Some objective, a short introduction on the Wigner function, on the orbit space. And then I will consider the metrics. I will speak about the Fisher information metric and also the monotone metrics. And finally, I will give an example of a qudit, as I promised. So as it was already said, the Wigner quasi-probability distribution is is a trace of the product of the density matrix, which is Hermitian, non-negative, and has a unit trace, and the so-called Stratonovich-Weyl kernel, which maps the elements from the phase space to the dual space. The master equations were presented recently by Vahagn Abgaryan. Why do we say that it's a quasi-probability distribution? The reason is that it has a very interesting property that for some states the Wigner function takes negative values. So it can be called proper statistical distribution, but quasi-probability distribution. So due to that very interesting property, we can indicate that it's some non-classical feature, it's some quantum feature. And from that, you can receive a lot of information. And today we will speak about the so-called global indicator of classicality. It's the ratio of the volume of orbit subspace of the states with non-negative Wigner function to the volume of orbits of the whole orbit space. So we have the Wigner function. We want to know where it takes negative values, or vice versa, where is it strictly positive. And then we calculate the volume of that domain, of that area. But to calculate the volume, you have to have metric. So we choose some metric, and as it turns out, the metric can cause the difference in the calculations. So the global indicator is very dependent on the chosen metrics, on the geometry, and that we will see later. So I will give you a short introduction because a lot has been said already. So the density matrix is presented in the block form, in the so-called block form, where psi is n square minus 1 dimensional block vector. Lambdas are the orthonormal Hermitian basis of SUN algebra. And to receive the Wigner function, you have to have two components. It's the density matrix and also the kernel, which is presented here by the SVD form, where k is a real parameter, and this k is Cartan subalgebra, and real coefficients mu live on the n-2 dimensional sphere. So we have to have n-2 parameters to speak about the Wigner function. So having these two ingredients, one can compose a Wigner function, and the dependence of the Wigner function from the so-called moduli parameter, the zeta, is encoded in this vector n. It's very interesting to note that having only this form of the Wigner function, we have in mind that our goal is to calculate the volume of the negative domain, or vice versa, the positive domain. We have to see where does this function takes negative or positive values, as you wish. And only from this form, one can easily verify that there is always a so-called R asterisk, is such a radius, inside of which the Wigner function is always positive. That's very interesting. That that means that if we choose the metric in such a way that its compact support will be in the ball of radius R asterisk, then the indicator would equal 1, and then it would mean that the Wigner function is a proper statistical distribution. So it's an extreme example, but that example helps us to understand that the matrix has a great influence on the Q indicator. So these are some definitions. Martin said about it a bit. Well, I'll just say that OP is the orbit space, well, this set is the set where the Wigner function is non-negative. That P plus is, of course, the subset of the P of the set of all density matrices. And, well, okay, that's enough. So the orbit space in this case is space where the eigenvalues are ordered in some way. Which way? It's your choice. But we choose the decreasing order of the eigenvalues, and you can choose some other way of ordering. It's up to you. So this is the so-called orbit space. This orbit, you can see that it's quite simple. For example, for a qubit case, a two-level quantum system, there will be R1, R2, so two eigenvalues of the density matrix. These are the eigenvalues of the density matrix. And you can easily see that you have just one equation and few inequalities. And you just get some line or some simplex, let's say, we call it simplex, for each case. And that simplex would be the orbit space. It's the orbit space. And what about the subspace? The subspace of non-negative Wigner functions. Well, we can show, but we won't do it today. We'll leave it for some PCA 2021, I hope. That actually this subspace is a dual cone where R's are the eigenvalues of the density matrix and P's are the eigenvalues of the Straton-Weyl kernel. And again, you choose the ordering, you fix it, and we also choose the decreasing order just for simplicity. And it turns out that the subspace OP can be written in this form. So you see R1 Pn plus R2 Pn minus 1, etc. And so this is the subset of the states with non-negative Wigner functions. So we have the subspace of the states with non-negative Wigner functions. We have the orbit space of the all states. Now we should calculate the global indicator. Now, my talk is about the metrics. Martin today was speaking about the Wigner function positivity. So we have two ingredients, let's say. The global indicator depends on the Wigner function positivity domain, and also it depends on the metrics that you choose. But how do you choose that metrics? What measures do you take? Well, for classical case, it's known that it's the Fisher information, and from the Fisher information, you have the Riemannian metric, and it's, well, let's say unique. But in quantum case, you have the analog of the Fisher information, but it's not that simple anymore, because we know that in quantum case, everything is more complicated than we would wish it to be. So having these two dependencies, we can speak about both of them, but now I will speak about the dependence on the metric. Here I give some very simple but healed up slide, and I don't want to stop on these slides a lot. I will just say the main idea, that the Fisher information matrix for the classical case gives rise to the Riemannian metric, which can be written in this form, and it has the analog in quantum case. In quantum case, it turns out that the metric should be stochastically monotone. So you can just choose whatever metric you like. So today I will compare a non-monotone metric, Hilbert-Schmidt metric, with monotone metrics, Bures and etc., and to see what's the difference between them. So now we're speaking about the quantum case. Let n be the set of all complex matrices. Let this second M be the manifold of all complex positive definite matrices. We can present the Riemannian metric on that M, called the monotone metric, as the following inequality. This holds for any density matrix from this M, from any U from the tangent space, and any completely positive trace-preserving mapping called stochastic mapping. In fact, the alpha lambda is monotone if and only if it can be written in this form. So F should be normalized, and it should possess this equality. From here, we can see that monotone metrics generalize the Fisher information metric. On the class of probability densities, it's a classical or commutative case, to the class of density matrices. It's the case of quantum or non-commutative case. These metrics, monotone metrics, are mostly used in quantum statistics and information theory. Today I will consider the so-called Bures, Bogolyubov-Kubo-Mori, Wigner-Yanase-Dyson metrics, and for each of them we have the so-called Morozov-Chensov functions. About that you may heard from Martin. So these are CB, BKM, and CWIYD. For the last case, alpha changes from -3 to 3, and for alpha equals ±1, we obtain the Bogolyubov-Kubo-Mori metric, and for alpha equals ±3, we obtain the so-called right logarithmic derivative metric, which is the greatest monotone metric with these functions. Well, these are just functions, and we're humans, so it's always easy to see some pictures. So here is just the picture of these functions. You can see that this Bogolyubov, this Buras metric, which is just a straight line, is the greatest one. The Wigner-Janasa-Dyson metric, which I plotted for alpha equals 3 or minus 3, it's the same result. It's hyperbola, this green one. And the intermediate case, which is the BKM metric, well, it's just mostly used in quantum statistical mechanics. Okay, so if we chose metrics, then we should get the measures to calculate the volume. So the respective metrics are of this form. Here is the dependence of the eigenvalues and the dependence of the Morozov-Chenzov functions. For each metric, each metric has its own function. So now I again write the formula of the global indicator of classicality for a n-dimensional quantum system is the following ratio. And we again see that the global indicator depends only on the domain of positivity of the Wigner function, these orbit spaces, and on the Riemannian metric that we choose, where dp is the corresponding measure. So now we will consider, if I have some time, a case of qudit, a case of three-level quantum system. It can be written, the density matrix can be written in this form. It's just very important to say that the qudit has 3 eigenvalues, and that's why we have this two-dimensional simplex delta 2. It's the space when the density matrix, the states leave, let's say. You can see that it's divided into 6 parts. They all are equivalent, but to avoid double counting of the density matrix, one should immediately choose one ordering of 6. So you see, if you have 3 eigenvalues, there are 6 possible ways to order them. We always choose one of them, not to count it again. So what are these lines? As I mentioned, I will consider the global indicator for low-dimensional cases. So I will calculate it not for the regular orbits, although it's also done, but yet it's just another task, let's say. Also interesting, but today I will speak about the 4-dimensional orbits. As you can see, there are 2 strata. So this one and this one. These are the cases where the first eigenvalue equals the second, but they don't equal to the third. And when the first and the second and the third are not equal, but the second and the third are equal. So these are the differences. It's always important to choose a convenient parameterization, and we choose this one. So from C3 and C8 we go to R and phi, and so this simplex, this triangle, let's say, goes to this region. This trisectories is called Maclaurin trisectories. Well, it's just an interesting coincidence. Again, having the density matrix, one should also not forget about the Stratonovich kernel to construct the Wigner function. And p's are the eigenvalues of the kernel, and they also should be ordered. And the convenient parameterization is chosen, from where we have this parameter zeta, which is also called the moduli parameter. And then we see that these p's live on this arc of a unit sphere. Since the Wigner function is composed from 2 Hermitian matrices, the density matrix and the Stratonovich kernel, it's bounded. You can easily see that the upper bound is always positive, so no information there. But if you look on the lower bound, you can gain some information. So you see that for these R's, the Wigner function is always positive. For these, it's always negative. And for some, it depends on zeta and phi. I'm only a few slides left, so we're almost there. So we will consider these metric measures in the simplex of eigenvalues. These are the forms for a qutrid case, where kf is a normalization constant, and for every case it's different. You see that the first case is Hilbert-Schmidt measure, and I'm saying that this measure is not monotone. We're interested in these cases, but we just, it's like to drink water before dinner, so we just do it. For the first type of orbits, when the first and the second eigenvalues equal, but the third is different, we get, these results are very complicated, so I just decided not to show it to you, otherwise it would be very long. But believe me that there are some expressions. And for the second type of orbits, it's okay with the Hilbert-Schmidt metrics, but these are zero. Why? Why is it zero? So here I write it why. These are zero because for these types of orbits, which include pure states, what does it mean, include pure states? Well, speaking strictly, it's this point. This point. It's the point of so-called pure states, maximally mixed. So the result is zero because they mostly accumulate states with pure close to pure ones, and so the function under the integral has a simple pole at this point, and the integral diverges. That's why these results are zero. And again, it's just simpler to plot it. This is the plot of these functions, but just q. But it's always more convenient to use the logarithmic one. So it's just the same plots. So the blue one, I'm sorry, it's too small. The blue one is for Hilbert-Schmidt measure 1, let's say. The second one, the orange one, is for Hilbert-Schmidt measure for the second type. And these are for the Bures and Bogolyubov-Kubomori metrics, respectively. So you see that indeed there is a dependence of the geometry, but the behavior is very much alike. So it's just a matter of numbers. So, saying the conclusion, the global indicator is sensitive to two features of classicality: the negativity of the Wigner function and local quantum uncertainty, which is accumulated in the form of geometric measure on the orbit space, inherited from a physically motivated quantum information content. So this means that when we choose a measure, the main goal is to gain the more information you can. So the information is in the states. The states are written in qubits, and to gain that information, you have to make a quantum measurement, let's say. So the more information, the better. Okay, so that's it, I guess. So thank you.
Okay. Ася, please describe in words what is going for the qubit, the simplest quantum object. This characterization of the.
Well, for qubit, it's just quite simple.
Yes, sure.
And
I am asking.
yeah, so there are only two eigenvalues, and the moduli space is just a strict line, not a triangle.
Straight line.
Yeah, a straight line. Here you can see the dependence on the parameter zeta for qtrit. But in a case of qtrit, there won't be any dependence on unknown parameter. Because, as I said, for a Stratanovich-Weyl kernel, there are only two equations that define the kernel. And for a qubit case, you have two unknowns and two equations, so it's just everything is fixed, no zeta, no parameter. Yeah. So the calculations are very simple, but I must say that it's not that simple as it may seem, because from the first glance you may think that for a qubit it's quite simple, because no entanglement, let's say, is just one particle. But it turns out that even for a qubit there is a negativity region of the Wigner function. Martin, it's 1 over square root of 3. So this block vector inside of which it lies, it's only positive Wigner functions, and the radius is 1. So you have a lot of investigation even for a qubit case. So you can make the same calculations for a qubit also, and you will gain a result because there is a negativity part of it.